Okay, well, let me start by once again thanking the organizers for inviting me to speak. It's been a lot of fun. Um, okay, so I just want to remind everyone what we're proving. So this is Baker's theorem. We're proving a slightly weak version, but the methods are exactly the same to pull the full strength version, which is that if we have algebraic numbers whose logarithms are linearly dependent over q bar, then in fact those logarithms are linearly dependent over q, and we're having to throw in 2 pi I because of sort of how we're deducing the linear dependence at the end. Okay, so let me just review quickly what we did last time because there's quite a bit of notation. So we showed that to obtain this conclusion that log alpha 1, okay, I see there's a chat question, but my mouse has disappeared, so it's hard for me to get to there. Okay, so.
I apologize. So I wasn't able to see the first page, so that's why I stood the question.
Oh, okay, yeah, that's okay. Can you see it now?
Yeah.
Okay, wonderful. All right, so I'll try to enter back to the full. Yeah, it's a little unfortunate. Okay, now that I have the chat page up, I shouldn't need to exit just to read the chat messages. Okay, it suffices to construct an auxiliary polynomial, which is the theme of this this conference. So we want to construct a polynomial whose degree is at most L, and for me that means the exponent of each term xi is at most L. And yet this polynomial has a bunch of roots of very special form. Namely, if I plug in my given algebraic numbers alpha 1 through alpha n, and I raise them all simultaneously to the zth power for L plus 1 to the nz, so this number of roots that I'm forcing myself to have is equal to the number of coefficients. So this polynomial, then we showed using a trick with the van der Waals determinant that this implies the conclusion of the theorem that log alpha 1 through log alpha n together 2 pi I are linearly dependent over q. Okay, so I'm not going to review that proof. I'm just going to remind us that that's what our goal is. Okay. And last time we introduced Baker's idea, which is you want to think of this function of f of alpha to the z, by which I mean alpha 1 to the z, alpha 2 to the z, all the way up to alpha n to the z. You want to view that as a complex analytic function of z. And what you want to ensure is not just the vanishing of this polynomial for a bunch of z's, but you want to ensure the vanishing of the derivative of this, because we're not going to be able to get enough z's as roots initially, but then by creating a lot of roots of the derivative, we're going to be able to do some bootstrapping argument in order to get enough roots of our original polynomial. Okay, so this was a little bit of review, some notation from last time. We used the given algebraic, linear dependence of the logarithms with algebraic coefficients. We used that. We expressed log alpha n as a linear combination with coefficients denoted beta I of log alpha 1 through beta n through log alpha n minus 1. So we could write this expression, the sum of p lambda alpha to lambda z, sort of in with n minus 1 terms rather than n. And that sort of, that's giving us the ability to create a polynomial that satisfies the following. So this is what we proved last time. And again, I won't review the proof. I'll just call the statement.
So sorry to interrupt. Sorry, I think our screen is lagging what you see.
Oh, what slide number do you see at the bottom of the?
2.
Oh, okay, yeah. So, oh yes, it's asking me, do you want to resume share? I don't know why sharing stopped. I don't know how to get this to occur, actually. Oh. Okay. I'm going to stop share and reshare because it doesn't seem to be working. I've noticed that, yeah, Keynote and Zoom, it's again saying screen sharing stopped. So do you see it now, right? But it's not in full screen?
Page 3, yeah.
Yeah. Jeez. But somehow, if I go into full screen, it And you're still on page 2?
We see page 3.
Oh, you see page 3. Okay, but now I'm going forward. It's still not showing. Okay, so I may just have to do this in not in the full screen mode.
Sure.
Okay, let me just try one more time. I'm going to quit Keynote. And then I'm going to load it up again. I apologize for this. I'm not.
It happens to all of us. We've all been suffering too. Digital talk giving this year.
Okay. Yeah, let me try one last time, and if not, with the full screen mode, and if not, okay, and if this doesn't work, we'll just, okay. Do you see page 3 now? Okay, wonderful. Yes, just often the solution technology is to quit everything and restart. All right, so apologize. So we are able to express this function, sum of p lambda alpha to lambda z, in terms of these n minus 1, the sum of these n minus 1 terms, log alpha 1 through log alpha n minus 1, with these coefficients, with the beta i's. And we were able to prove the theorem that there exists a set of coefficients that defines our polynomial f, and hence defines our function phi, satisfying the following properties. So the coefficients are bounded by, e to the h cubed, so an exponential in h cubed. The degree of the polynomial is h to the slightly less than 2, so 2 minus 1 over 4n. Remember, n here is the number of our alphas. Okay, and we get the vanishing that we desired. So the first m derivatives vanish for all z's all the way up through h, as m goes from 0, 1 all the way up to h squared. Okay, and so we'll see why these parameters turn out to be useful in a moment. But just a reminder, we prove this using what I call Siegel's lemma, which is basically a fancy version of the pigeonhole principle. Okay, and so that did advance, right? To the next slide. Okay, good. All right, so now the first thing that we wanted to apply this lemma that I called Baker's lemma, which is just some upgraded version of Schwarz's lemma from complex analysis. And in part of that lemma, the assumption was a bound on f of z that was of the form e to the power of a constant plus a constant times the absolute value of z. So we want to get a bound for our functions phi in that form. And again, we're going to do some trick where we show that a function is small, and then we show that it's actually 0 by noticing that it's actually algebraic, and algebraic numbers can't be too close to 0. So we want to separate, when we calculate the nth derivative of phi, so we want to separate sort of something that's purely algebraic, that has only algebraic aspect to it, with stuff that is not necessarily algebraic, like these logarithms of the alphas. So let me actually go back. Oops. Go back to the definition of phi for a moment. What happens if you take the derivative of this? Well, this thing that you're multiplying z by comes down to an m times. So you get this expression in square brackets raised to the mth power. You multiply that out, you get a multinomial coefficient. You'll then get, this lambda 1 plus lambda 2, lambda n beta 1 to the m1 power, all the way up to this term to the m sub n minus 1 power. And then you'll get a product of the log alpha I. So that's all I was showing on this slide here. So if you multiply out, then you get this multinomial coefficient, you get the log alpha i's to those powers. And then what's left will be exactly what I just said, the lambda 1 plus lambda n beta 1 to the m1, dot, dot, dot. And the point of writing it this way is that this fm, if I plug in an integer value for z, this is an algebraic number. Okay, so this is kind of the purely algebraic part of our expression. All right, and we just want to note that there is a bound on this, and you just use a trivial bound. So the alphas are some constants. So k is just some constant here, depending on the alphas and the betas and n. So as long as k is bigger than any of these alphas, then that, and lambda is at most L, then this will be at most k to the lambda times absolute value of z in magnitude. These other terms, they're smaller. The lambdas are at most L, and the m's are at most h squared. So this is at most L to the power h squared. Well, I guess there's a constant involved here also, but basically L times a constant to the power h squared. And how big is L? L is also h to the almost h squared. It's h to the 2 minus something. But anyways, it's a power of h. So I have h squared to the power of h squared, which is like exponential of h squared log h. Okay, which is the point is it's still less than h cubed. So this h cubed kind of dominates anything that actually occurs in this expression. Okay, and then the coefficients were exponential of h cubed. Okay, so there's a universal bound on this for all z's of k to the h cubed plus L times absolute value of z. Okay, so now we're going to apply this Baker's lemma, and again, I don't expect everyone to follow all the details live in a talk, but I'll put the slides up later, and I try to make the slides so that you can actually check all details by looking at them later. So let me just point out what I think are the salient features here. So remember, this was the kind of bound we needed in the proof of it. This is Baker's lemma. The bound that we got is e to a constant plus a constant times the absolute value of z, and the conclusion was sort of decaying faster than that. So it's e to that same power times something that's a log a to the 1/2. So if we can ensure that our what we plug in for a is large here, we can ensure that this is multiplied by this, and maybe multiplied this by some power, some constant power, will still be less than 1, which will enable us, if I plug in an algebraic argument, to show that it has to be 0. Okay, so this was Baker's lemma, and if you check that we rigged all the coefficients to satisfy sort of this complicated inequality, which we go through the details of last time, if you choose the right parameters. So remember, the point is we choose a k such that our absolute value of f sub m1 through m sub n minus 1 was valued by an exponential of k to the h cubed plus L absolute value z. Now just check that if you plug in these values for the parameters in this general lemma that we proved, h cubed log k, lk, etc., that we get this condition satisfied. Okay, so this condition is what I just said, right? So t is h cubed log k. That means e to the t is k to the h cubed, and etc. So this is exactly the bound on my f's that I gave you in the last slide, which is repeated here. Okay, so the t and u give me this bound. It's just the variables that you need. And we want to apply this not just to f, but to a bunch of derivatives of f. So we'll take half the derivatives that we started with, say h squared over 2, and then this is true for up to the h squared over second derivative, right? So if it's true all the way to the h squared the derivative, then for each of the first h squared over 2 derivatives, it's true for their first h squared over 2 derivatives. So I can take my c, this is the number of derivatives I'm taking, to be h squared over 2, and then apply this not just to f, but to the first h squared over 2 derivatives of f. Okay, and then the constants you can use a is h, and then this 1 over 8n comes from our L was h to the 2 minus 1 over 4n. This is going to get squared somewhere, and you need it to cancel out the 1 over 4n. So okay, and epsilon is 1 over 8n. Then you can check that the inequality holds. And again, I don't expect you to check this live. The punchline is all the parameters have been chosen so that it works out. The left side is on the order of h squared. The right side is on the order of h squared divided by log h to the 1/2. So there's an h cubed here. There's an h log h to the 1/2 here. You get h squared over log h to the 1/2. So the point is you can take h sufficiently large that the left side is bigger than the right side. So this holds for h large. And then what does the lemma yield? The lemma yields a very nice upper bound on what these values can be for an expanded number of z's. Okay, so you started with this the fact you had vanishing on z going all the way up to a, and my a was h. Okay, that's right. That's how we started with h zeros. but then we're going to sort of expand that by a factor of h to a power. It's a small power, maybe if n is large, but it's still h to a positive power. I mean, we can get that f is small. Oops, skipped ahead more than I want. We can get that f is small, this bound that is, where the exponent is even better than the upper bound, and it's a negative, for an expanded number of z's. So you can go all the way up to z, going up to h to the 1 plus 1 over 8n. Okay, and now we use this trick of sort of what I call discreteness of the algebraic integers. Can someone read me the chat? Because if I go to this chat, I'm worried I'm gonna lose everything.
I'll just ask my question. Could you remind me why the exponent 2 minus 1 over 4n is important?
I think that will show up later. I don't remember if we already used it, but I actually know we did. I think I did point out last time we needed it to be less than 2, right? And we got it to be less than 2 because using this algebraic dependence over log alpha i's. I forget if it's going to get used again. We'll look out for that. But the point is, it has to be positive. It has to be positive. It has to be less than 2.
Okay. Thank you.
Yeah, sorry if I didn't quite answer that. Maybe we can go forward. Okay, so I don't know if I said everything on the slide. So the point is, right, so we have this upper bound on the value of the f's, okay? And now if you look at all the conjugates of f, if you go back, what's the definition of f? Okay, the conjugates of f are just, you need to conjugate the alphas and you conjugate the betas. So it's going to be another expression of the exact same form. So the same method we used to describe, and it was just a naive method of giving an upper bound for this, just taking an upper bound in every individual term. That upper bound will give us the same upper bound for all the conjugates of f. Okay, so the conjugates of f are all bounded by the same expression without this factor of log h to the 1/2. Okay, so when you multiply them all together to take the norm, you can make the product less than 1. And furthermore, if you go back and check, you can, these are algebraic numbers, not necessarily algebraic integers, but the denominator can be cleared by an integer also of this size. So it's not hard to go back and check. Okay, so again, if you multiply it by this kind of constant, even to a constant power, it'll be like the nth power, or whatever the degree is of the field generated by these alphas and betas, it'll be some fixed power. Then even if you multiply, something of this to some fixed constant power, as long as h is large enough, this log h to the 1/2 is going to dominate. The product is going to be less than 1, but this is the norm of an algebraic integer, so if it's less than 1, it has to be 0. So it follows that actually these functions f sub m1 through mn minus 1 is actually 0 for all of these z's. And what z's did I take? I had a slightly expanded version of number of z's. I had z going from 0, not just up to h, but to h to the 1 plus 1 over 8n. And I know this, so there's a typo here, right? So, oh, no, this is right. Sorry, no typo, right. So f sub, right. So this is true, not just for my original f, but all these f sub m's. And now I have half as many f sub m's that I had before. So I sort of started with order of vanishing h squared at all these points 1 through z equals 1 through h. And now I'm getting vanishing not all the way up to h squared derivatives, but up to h squared over 2, because I need each of those derivatives to have h squared over 2 derivatives to make this argument work with the property. So for half as many derivatives, you get an expanded amount of vanishing. Okay. So now you just do it again. Now you bootstrap. So now you have more zeros, right? We started with h zeros. Now you have h to the 1 plus 1 over 8n zeros. Okay. And now you just do it again. So this is a k. You do it k times. So now you see why I use general parameters instead of just plugging the actual values I used into the original lemma, because I want to do it again with new values for the parameters. So these are the adjustments that you take in the values of the parameters. And again, you scale the amount of zeros or the number of zeros you're scaling by is always this h to the 1 over 8n. So then there's the number of zeros you start with, is the number you're scaling by. So it just sort of adds an h It adds an h to the 1 over 8n, or multiplies by h to the 1 over 8n each time. So it adds an 1 over 8n each time. And you can just keep repeating this process, okay? And then eventually you'll get h to the 2n roots, okay? And since L was h to the 2 minus 1 over 4n, we have h to the 2n is greater than L to the n, which gives us more roots than we had coefficients. And we can then apply our trick about Vandermonde. So we've produced our auxiliary polynomial with more roots. So it's polynomial that a priori only had roots up to sort of h, which is much less than the degree to the n. Actually, at the end of the day, using the vanishing of the derivatives, you see that it actually vanished to many more z's than you thought. Okay, so this completes the proof. And because that sort of extended over 2 days, I just want to give a summary before we end and move on to another topic. So we started by using the box principle or pigeonhole principle to construct a polynomial f of x such that it and many of its derivatives, right? So it's the number of derivatives was h squared, and h was this parameter that we took very large. So this many of its derivatives vanish at alpha to the z for a large, but not quite large enough, say a collection of integers z. And this uses the existence of the algebraic linear combination of the logs that vanish. Yeah, so I apologize, I didn't answer the question that was asked me because I think I used it in the previous talk. Okay.
Didn't we just use it on the previous slide in the last line or 2 slides back?
I think I'm not sure.
Right
Yeah,
there.
right there.
We used it.
Yeah, but somehow I think you can just go further and keep bumping this up. If this was slightly larger than 2, this part of the argument I don't think really uses it, because you can just I think you're right, actually. You know what? You're right, because let's look here. I think you need this u to be less than h squared. You need sort of u times, you need, right. Okay, when you check this, so it's in part of it is in part that I glossed over. You need u times b to be less than, if you check that inequality, you need u times b to be less than t or something like that. And you have an h to the 2 minus 1 over 4n, this is why you can only go up to h to the 1 over 8n at each time. You multiply them, you still get h to the 2 minus 1 over 8n, which is less than h squared. Sorry, you need u times b times h or something needs to be less than. If you check the inequalities, you'll find where another place you need it. But I think I did use it last time also. Okay. All right. But yes, I don't think it's literally in this last step, because we're just bumping the exponent up by 1 over 8 at each time, and eventually you can get over whatever you need. Okay. Okay. So anyway, so the step 1, use that algebraic linear combination of logs that vanishes, exactly in order to get that exponent less than 2. The second step was to use Baker's lemma to deduce that half as many derivatives of f of x are tiny for b times as many integers z for some, cleverly chosen b. Then use the discreteness of the algebraic integers to show that these tiny values must actually be 0. Okay, so now you have more vanishing, but maybe still not enough. But then you just iterate. So then, armed with more vanishing, you go back to step 2 and say we have even more vanishing. So that gives me a better bound using Baker's theorem, which means that more values are small, and then those small values also have to be 0. And then you keep going until you get enough zeros. So after iterating n times, such that each time you're multiplying by a factor of b, that a times b to the n is greater than the number of coefficients that you started with, then you conclude that you have a polynomial with more roots that could be allowed without having this kind of rational dependence of the logs. So that's the full proof, and this invoking the use of the derivative is sort of a major idea introduced by Baker.
So we have a question. I'll just read it so you can hear it. It says, is there any quick way to see that by doing the calculation, the argument goes through, at least an intuitive justification why such an argument is enough?
Why such an argument is enough?
I guess like a rule of thumb.
A rule of what?
A rule of thumb?
A rule
I
of
think the
thumb?
person's asking for.
Yeah, that's a good question. I can't say that sort of it's clear to see that. I mean, the point is the algebra, sort of it's the algebraicity of the linear dependence they start with that's very important, which allows you to show the vanishing from the fact that the function is very small. The only way that I can really explain, like sort of intuitively, is to work on another problem and to see, oh, if I had algebraic coefficients, it would have been really great, and which is the next problem that I'll be discussing. Yeah, I don't know. I mean, it's a little bit of a miracle, and it was viewed as a huge miracle when Baker proved this. He won a field medal for it. This idea of introducing the derivatives. I guess, I mean, the short answer is, I mean, I don't know as a rule of thumb. I mean, somehow it's when you have these, the reason the derivatives work nicely is when you have this exponential, right? And you take the derivative and the factor comes down, that the fact that the coefficient you get there now, these betas are algebraic, is great. So the point is, okay, so here's one point I can make. What's really hard is bounding the size of these things, right? Because you have you have alpha to the z, and you want lots of z's, but then when z gets bigger, this is growing exponentially, right? As z gets bigger, you have an exponential in z. So you want to make something small, right? You want bounds on sizes of the things, because the way that we show algebraic things are zero, we show that they're small, right? So you want to prevent things from growing too large. So it would be great if we could do that. And so the derivative gives you a trick of showing more things vanishing without increasing the size too much. Because when you take the derivative, that's another function that's of basically the same size. That is, you don't have to make z larger, you're just saying that I'm taking more derivatives, right? So the exponential in z, that part is being the same. When you take the derivative and you knock down the coefficient, that's not an exponential anymore. So it's not growing. So the size of the derivative is about the size of the original function. So you can take basically the same number of z's, which is, you know, the z growing is what's making the thing large, which makes it really hard to show that it's zero. By taking a derivative, you can show more things are zero without increasing their size, okay? And then the fact that the thing that you're bringing down is still algebraic means that you can show it's zero. So that's why having this algebraic linear dependence is very useful for showing something zero, and why it maybe is natural to think of the derivative, you know, in retrospect, after he's shown us to do it, is because you can show the derivatives are zero because the derivatives aren't growing super fast. They're growing at the same rate as the original function. So for the same set of z's, you can show that the derivatives are vanishing. I don't know if that was helpful, but
yeah, interesting.
Yeah. Okay, so let me move on. All right, so what's the topic basically for the remainder of my lecture series, and what sort of really got me interested in this topic is not just linear forms and logarithms, but more complicated forms, say quadratic forms or higher degree forms. And I'm going to look at things of a particular form, being determinants of matrices. And in fact, I'll describe a theorem today which says that this kind of contains most of the story, or a huge part of the story. Okay, so so let me just start with the simplest case of what I'm interested in, which is the 4 exponentials conjecture. And I find it wild this is still open. It's a big open problem in transcendence theory. So suppose we have 4 algebraic numbers such that when I arrange the logarithms in a 2x2 matrix and I take the determinant vanishes. Okay, so this is a sort of a quadratic form in logarithms rather than a linear form. Okay, then the conjecture is that either the rows or the columns of this matrix are linear dependent over Q. Okay, of course, they're linearly dependent over C because that's linear algebra, but the conjecture is they're linearly dependent over Q. Okay, right? So it's kind of, there's a silly way to make a matrix whose determinant is 0. I can do that right away. Okay, so that's a 9. Right, so that matrix has determinant 0 because the second row is twice the first row. But the punchline is that's basically the only way to do it. Okay, is that to have a rational linear combination of either the rows or the columns. And we don't know how to prove this, but we know how to prove a partial result, and I'll describe the general theorem of the more general theorem that implies this partial result today, and then we'll prove it next time, which is the 6 exponentials theorem, which says, okay, if I give myself a 2 by 3 matrix, so 6 exponentials, and you assume that the rank is less than, the biggest it could possibly be, which is 2, so the rank is either 1 or 0, then either the rows or columns of them are linearly dependent over Q. Okay, so this is over Q. All right, so this is the partial result. And now you might think that this generalizes higher dimensional matrices, but it's not true. So for 3 by 3 matrices, if you think that a matrix 3 by 3 matrix of logarithms of algebraic numbers, that the determinant vanishes, then the rows or columns have to be linearly dependent over Q. This is false. Okay, and there's this very famous example given here. Okay, I'm being slightly cheeky. This is not a famous example, and this is not some weird coincidence of logarithms, algebraic numbers matching up in some fancy way. These are random numbers I picked, and it's a trick, which is that there's an algebraic reason why this is true. You've just plugged in log 7, log 29, and log root 2 plus 1 into some algebraically, determinant that's algebraically equal to 0, and you can check that the rows and columns of this matrix are not linearly dependent over Q. So it's probably not going to happen for this matrix up here. I tried to be a little bit clever by putting this logarithm that looks different than this logarithm, but this number is just the inverse of this. There's my x to negative x. So this is just algebraically true. And the general conjecture is that this is what's going on, which is that once the logarithms are linearly independent over Q, then they should behave like algebraically independent variables. So that's called the structural rank conjecture, which I'll present on the next slide. Okay, so let me present it in a slightly more general way. So let's say I have an extension of fields and I have a matrix, an m by n matrix, does not have to be square, with coefficients in the larger field. And we take an f basis for the f linear span of the coefficients of this matrix. Then I can write m as a linear combination sort of these basis elements where the thing of these mi's is the coefficients are matrices that are m by n matrices over the ground field, the smaller field f. And then I replace these linearly independent elements, ci, which are in my bigger field, k, I replace them by formal variables, by algebraically independent variables over f, which I call xi. So these are indeterminants. And so now I replace them and I get a matrix that I'll call m sub x, which is an m by n matrix in just the field of functions, f adjoint, x1 through xk, this k independent algebraic variable, independent variables, algebraically independent variables. Then the structural rank of m over f is the rank of this matrix, in these formal variables over this field. Okay. And it turns out you can show this is independent of the initial basis, f basis of this f linear span of the coefficients of m that you started with. So what's going on is that the structural rank of this tricky matrix that I started with, the structural rank of this over Q is actually 2. It's not 3. They're sort of the determinant vanishes algebraically once you replace these linearly independent logarithms, log of root 2 plus 1, log of 7, log of 29 with indeterminants, then you get a matrix of rank 2 over the field, Q adjoin x, y, and z. Okay, and so the conjecture is that in general, the rank of this matrix, when you plug back in the logarithms, has to equal whatever that sort of formal rank is, structural rank. That's the structural rank conjecture. So I've already stated the conjecture. Okay, so let L, so this will be a notation that might come in handy later. L is the set of logarithms of algebraic numbers. So this is sort of this numbers we've been thinking about. This is a Q vector space, Q vector subspace of C. And the conjecture is 5 any matrix with coefficients in L. In fact, there's a slightly more general statement where you take L and you throw in, the subspace spanned by 1 into it. So it's actually more general than just taking m cross n of L. That the rank of this matrix is equal to the structural rank of m over Q, as I just defined it. So you place all these logarithms, you take a basis of the span of the set of logarithms over Q, and you take and you replace all those logarithms with indeterminates. You take that rank. That's supposed to be the rank of the matrix when you plug back in the logarithms. Okay, this plus q is very similar to how I said in Baker's theorem, you get a stronger result, which is that 1 and the logarithms of the algebraic numbers are actually q linearly independent. So this is kind of very parallel to what we saw when I didn't prove this, of course, but when I stated the strengthenings of Baker's theorem that he actually proved, this is very parallel to that. Okay, and I just want to mention there's a version over q bar, which is you replace q here by q bar. So you take q bar linear combinations, q bar L's, q bar linear combinations of elements of L. So the q bar vector space spanned by L, place this q by q bar, then the rank of M is supposed to equal the structural rank of M over q bar. And there's an amazing theorem of Damien Roy, which says that the first conjecture implies the second conjecture. And the reason that it's amazing is that it's not obvious at all. Like if you just follow your nose and you give yourself a matrix with coefficients in q bar L, and you try to apply the conjecture, you try to sort of cook up some other matrix with coefficients in just L, and you try to apply this result to it and then deduce this result to it. I don't think it'll work. Like that kind of follow your nose kind of strategy doesn't work. And the fact that this is true and is very deep and provable is kind of amazing to me. And I think it's a fantastic paper by Damien Roy. If you're interested in that, I'm not going to have time to talk about it. I gave a course on transcendence degree, the videos of which are on my webpage, and I think it's lecture 7, I want to say, where I prove this theorem of Roy. It's kind of fantastic. Okay. Now, it'd be remiss if I didn't say that this conjecture, the structural rank conjecture, is a special case of kind of the uber conjecture of transcendence theory, which is known as Chanuel's conjecture. So Chanuel's conjecture states the following, which is that if we have any complex numbers, n complex numbers, I'm not assuming they're algebraic or the logarithms of algebraic, whatever, there's any complex numbers, okay, but I'm assuming they're q linearly independent, then the transcendence degree over q of the field I obtain by adjoining all of these elements with their exponentials is at least n. Okay, so if the yi's are algebraic, then this is known. This is called the Lindemann-Weierstrass theorem. So then the yi's go away because they're algebraic, and I get that the transcendence degree of the exponentials of n algebraic numbers as transcendence degree n, and that's the known theorem. Okay, but the other extremal case where the exponentials are the algebraic numbers, so the yi's are logarithms of algebraic numbers, so then the e to the yi's go away because they're algebraic, and you're asking for the transcendence degree of q adjoin n linearly independent logarithms of algebraic numbers, that transcendence degree is n. So that's very much not known. Okay. And this other sort of extremal case, this turns out to be equivalent to the structural rank conjecture. Okay, so somewhat surprisingly, this particular conjecture about ranks of matrices turns out to be equivalent, and in fact, the square matrix case turns out to be equivalent to this sort of really important special case of Chanuel's conjecture. Okay. And this is also a theorem of Damien Roy. And so this theorem I am going to prove. So the structural rank conjecture is equivalent to the special case of Chanuel's conjecture, i.e. the algebraic independence of logarithms of algebraic numbers that are q linearly independent. Okay. And I should mention there's the p-adic versions of all this, which I won't really get into in this course, but I'll just mention because of its importance in algebraic number theory and sort of Iwasawa theory. I'll mention some of this later. The importance is that the p-adic structural rank conjecture is equivalent to the p-adic version of the special case of Chanuel's conjecture. Okay, and here's the picture of Damien Roy. Okay, so let's prove this theorem. All right, so this is not the first theorem I stated, but the second theorem. This is the equivalence between the special case of Chanuel's conjecture and the structural rank conjecture. All right, so could someone read me the chat question?
I don't see it. Oh, sorry.
Oh, okay.
It didn't mark it. Sorry. Okay, here's one. when you state this equivalence between the structural rank conjecture and the special case of Chanuel's conjecture, do you mean that the structural rank conjecture for n by n matrices is equivalent to the special case of Chanuel's conjecture for n?
No, I think we're going to use matrices that are not n-dimensional. Well, I'm sure we're going to use matrices that are not n-dimensional in proving the special case of Chanuel's conjecture for n elements. We need to know the full conjecture. Okay, all right. All right. So one direction is not difficult. So I think actually, okay, so maybe one direction of that equivalence is okay right here. But the hard direction is we need the full structural one. Okay, so assume the special case of Chanuel's conjecture is true, and suppose that we have right, you write your matrix as a linear combination. So MI/CI, where the MI's are matrices over Q, and the CI's are linearly independent elements of L. So I think right now I'm just doing the case of L, not L plus Q. I said this is a sort of slightly stronger version was true. I'm just dealing with L here. Okay, so you have MX, which is the sum of MI times XI. So you've replaced these CI's with formal variables, and we let R be the rank of this matrix. So what is the rank? Well, one of the definitions of rank, maybe not the best one, but convenient for this purpose, is we know that if the rank is R, that there is an R by R submatrix of this matrix M whose determinant is non-zero. So we view that, so we consider the determinant of that submatrix, that minor, as a polynomial. So it's a polynomial with coefficients in x1 through xn. And the determinant of the corresponding submatrix of M is by definition what you get when you plug in Ci for Xi. So it's just P of C1 through Cn. And hence it can't vanish since the Ci are algebraically independent by the special case of Chanuel's conjecture. And therefore the rank of M, because M now has an R by R submatrix determinant is non-vanishing. We know the rank of M is greater than equal to R. But of course it's clear that the rank of M is less than or equal to R, to the rank of the formal thing, okay? The rank of a specialization, right, of a formal thing can go up. So you have the reverse inequality. So you get equality, right? So this direction is kind of clear, and it's just that sort of determinants of a matrix with these coefficients will give you some polynomial. Okay. So I'm going to skip these slides for time reasons, but I knew I would have to do this. I just put them in because people can download the slides and look at this. You can generalize the argument I just gave for L plus Q. It's slightly, a little bit technical, but there's an adjustment. Okay. Now let me talk about the converse, and the converse is more interesting. And again, I'm not going to have time to prove this lemma, which I think is what someone was alluding to in their question, which is. Okay, so suppose you have the structural rank conjecture, and now you have C1 through Cn and L, right, the linear independent of Q, and suppose that they actually satisfy some polynomial with coefficients in Q, okay? Then you want to cook up a matrix that for which you can then contradict the structural rank conjecture, right? And the key lemma is this, that there exists a square matrix N with coefficients in Q plus Qx1 through Qxn, whose determinant is P. If you're watching this lecture and you want a fun exercise, I encourage you to try to prove this lemma before the next lecture when I will prove it, because it's not easy. Well, at least I tried, and I just got frustrated and emailed Damien and said, "How do you prove this lemma?" So it's fun. Okay. So, all right, so let's just assume that lemma. So now let M be this matrix whose determinant is P, with Xi replaced by Ci. So then you have the determinant of M is 0 because it's P of C1 through Cn, which we assumed was 0. Okay, but now we have to use the structural rank conjecture for this matrix M, okay? And now the matrix Mx and the structural rank conjecture is the homogenization of the matrix N, the original matrix, let's see. So this matrix n has coefficients here. The point is there's this q, right? And that wasn't in our initial discussion of the structural rank conjecture. So you get a variable when you look at the definition of structural rank. You have to put a variable there, right? So you're going to get an extra variable somehow. Okay. So, and by the way, we're using the fact that 1 has to be linearly independent from the logarithms of these algebraic numbers, which is basically saying that E is not an algebraic number. Okay, so we're using that to say that I can take a basis with 1 and then these other CIs. So that's what tells me that when I take the basis of 1 and the CIs for the coefficients, that I can put an x0 there. Okay, so that sort of 1 is one of my basis elements. Okay, so the structural rank conjecture implies that the determinant of this matrix mx is 0. Okay, but then, okay, so then I just specialize that x0 back to 1. If this is a polynomial of x1 through xn, that's 0. Then if I plug in x0 equals 1, it's still 0. And then then plugging in x equals 1 gives me back, my original matrix x. Okay. But the determinant of n was the polynomial p that I started with, that vanished at c1 through cn, so it can't have been 0. So that's a contradiction. Okay, so this is pretty easy actually. This argument, it's just kind of a formal argument. The key lemma is this one, which I did prove and left as an exercise for you. And if I have time next lecture, I'll prove it. In any case, I'll put it in the slides next time, whether or not I have time to actually prove it. Okay, so the time. Okay, so in the time that I've left, I want to talk about what is our strongest evidence towards the structural rank conjecture, which is a theorem of Waldschmidt and Masser, okay, which states the following, which gives us kind of a lower bound on the rank, which is not, not the expected one, not the one that structural rank tells you, but it's kind of, it's basically like for a square matrix, it's basically half what you expect. Okay, so let's say you have an n by n matrix, and suppose the rank of m is less than n over 2. Okay, so the rank is, at most half what it could be. Then there exists sort of a change of basis on the right and the left, so on the image, on the domain and codomain, a rational change of basis on the domain and codomain, so that when you put the matrix in that basis, you get a huge chunk of zeros. You get a block matrix with an upper right corner of zeros where the dimension is large. So it's m by m prime. And one thing that's interesting is you don't get control on either, dimension, and in particular m or n prime, but you see that it's large in the sense that the sum of the dimensions is larger than n. It's larger than the dimension of the matrix. Okay. So in particular, m and n prime are at least 1. But so one way this could happen, so like you could get maybe a 2 by n matrix, and so you'd have 2 rows of zeros, which of course would one thing to note is that somehow that implies this block of zeros is so big it automatically implies that the determinant of the original matrix m is 0. Of course, you're assuming that anyways. You're assuming that the rank is less than half, but that kind of principle will be useful for us when we do some clever arguments in a moment. So, okay, so one thing to note is that the conclusion is so strong, this huge block of zeros, that it's not clear how to generalize this right away to say that, okay, if the rank is just maybe you just expect the rank to be n, and you want a statement that says, suppose the rank is less than n, then I have some conclusion, right? So you can't hope to conclude something as strong as this, because this implies something very sort of strong about the matrix, which doesn't necessarily hold just if the determinant vanishes. Okay, so that's kind of a segue into some topics of open research, which I'm thinking about. But let me get back into this Waldschmidt-Masser theorem. Okay, let me state the general version for non-square matrices. So let's say you have an m by n matrix of logarithms of algebraic numbers, and suppose that the rank is less than mn over m plus n. So when m is equal to n, this is just m over 2. This is the general formula. Then again, you have a change of basis on the right and the left, a rational change of basis, such that you get this big block of zeros, and maybe it's actually even slightly more elegant to how you write this condition is that sort of the proportion of the rows plus the proportion of the columns that you get is greater than 1. It's larger than 1. Okay. So I'll say, so the first corollary is the theorem that I stated earlier, the 6th exponentials theorem. So if I have a 2 by 3 matrix of logarithms of algebraic numbers, and suppose that the rank is 1, then either the rows or columns are linearly dependent over Q. And you see that these numbers work out very nicely. 2 times 3 over 2 plus 3 is 6/5. And so since the rank is less than 6/5, there exists a change of basis on the right and left, such that you get this big block of zeros in the upper right hand corner. Okay, there's not too many values for what m prime and n prime can be. If m prime is 1, then n prime being greater than 3/2 means it's at least 2. If m prime is 2, then n prime has to be greater than 0, which means that it's at least 1. So either way, you check if you have a 1 by 2 matrix or a 2 by 1 matrix of zeros in your original matrix, then that means that your rows or columns are linearly dependent over Q. Okay, so there's a corollary. And so I'm going to prove that next time. And the remaining time that I have today, I want to just talk about some applications of this to number theory, just for people wondering why I'm interested in this. I'm an algebraic number theorist. So I thought I would just describe that. So let's fix an embedding of Q bar into the CP, which is this, what some people call the p-adic complex numbers. This is, you take the algebraic closure of QP, and then you take its completion. So unlike R, when you take the algebraic closure of R, it's still complete. Back to this Archimedean topology. But if you take the algebraic closure of QP, it's not complete anymore. So you have to complete it, and that's usually what people call CP. It has nothing to do with the usual complex numbers, even though people use that letter C. It's supposed to be the analog of the complex numbers in the p-adic setting. Okay. Anyway, so we just take some embedding. I probably could have just done this with QP bars, but people usually like to write CP. So. All right, so now let F be any number field. So this is a finite extension field of the rational numbers. It has degree n, and I denote the n embeddings of F into Q bar by sigma 1 through sigma n. And now let's take a basis for the unit group modulo its torsion, which is the group of roots of unity. So this is a finally generated, this is a free abelian group now, finally generated free abelian group of rank R, and R is R1 plus R2 minus 1 in the usual notation. R1 and R2, the number of real and complex embeddings, respectively. Okay. Then we just take a matrix. So this is a matrix of logarithms of algebraic numbers. So it's the kind of thing that's showing up in the previous slides, where we take the p-adic logarithm. So I haven't defined this, but there's a p-adic version of the logarithm. And again, I'm not going to do much with the p-adics and the rest of this. I just want to give this application to what we're talking about. You take the p-adic logarithms of sort of the images of all these units under all the embeddings. Okay, so once I've embedded F into Q bar, then I've fixed one embedding of Q bar into CP, I can view this as an element of CP, and then I can take its p-adic logarithms. Okay, p-adic logarithm is defined on CP star. Okay. So then this is an R by N matrix in what I will call LP, which is p-adic logarithms of algebraic numbers. Is it Q vector space, or I usually take the Q vector space generated by those things. Anyways, then the conjecture, Leopold's conjecture, is that the rank over CP of this matrix M, this matrix of p-adic numbers, is R. It's maximal, right? This is an R by N matrix, so you want to have rank as large as possible. It's R. Okay, and this is a very deep and very important problem in number theory. So I guess yeah, I think I'm not going to have time to go over these slides, but again, I'm going to include them. So if anybody's interested, they can look back. I give some applications of this conjecture. Sort of algebraically, it's used in Iwasawa theory, which I study, and also the theory of p-adic L functions, which I also study. So I'll just say that there's a p-adic, this is kind of cool, so I'll say there's a p-adic zeta function that interpolates values of the classical zeta function. And there's a theorem of Kolmez which says that just like the classical zeta function, there should be a pole at s equals 1. What he proved is that the limit as s goes to 1 of s minus 1 times the zeta function is some non-zero constant, which is explicit, times a p-adic regulator, which is the determinant of the matrix that I just gave on the previous slide. So as long as one knows this is non-zero, then sure enough, that means this has a simple pole at s equals 1. The problem is this could be 0, and that could be telling us that actually this is regular, has no pole at s equals 1, but is regular. So it's kind of amazing that in p-adic number theory, we don't know that the p-adic zeta function has a pole at s equals 1. I mean, we do for Q, okay, but for a general number field, we don't know that.
And this matrix is square in this special case considered here?
Well, yeah, so you do the standard thing where you kind of eliminate, right? So in this case, it would technically be sort of r by r plus 1 the way that I defined it, because the unit rank, the rank of the unit group of a totally real field is 1 less than the degree. So you do the standard thing if you just cross out any one column and to make it an r by r matrix, right? So you just, the sum of the rows is still 0 because it's the log of the norm of the unit, but the norm of the unit is 1, so the log of the norm is 0. So the sum of the rows is 0. So you cross out any one column and you get a r by r matrix, and you take its determinant. Yeah. So thank you for correcting me. I said it was the determinant of the matrix in the previous slide. That's not quite right. You have to cross out one of the columns. Okay. All right. Over. Okay. So I'm running out of time, but this is pretty much what I want to say. So I wanted to prove that Leopold's conjecture is implied by the p-adic structural rank conjecture. You can look at that next time in the slides if you're interested. But what I'll end with is just that the reason I'm interested in this Walsh-Master theorem is that this is the strongest evidence we have toward Leopold's conjecture. Okay, and I wanted to give this kind of proof that I alluded to earlier, which is so the theorem given the Walsh-Master theorem is that the Leopold regulator has rank at least half what you expect it to have. So you expect to have this rank r, which is the rank of the unit group. It has rank at least r over 2, and that's sort of the best we know. Okay. So let R be the expected rank of the Leopold matrix, which is R. It's an R by R matrix. So again, I've sort of crossed out one column here so that it's a square matrix, so that the determinant of that submatrix is oh, sorry, I'm doing this in the general case where it's not necessarily a totally real field. So let me not just say one column. But anyways, let's let R be the expected rank of the Leopold matrix, which is the rank of the unit group. So it's for a general number field. And then you take any R by R submatrix then of the Archimedean regulator who's determined as non-zero. So remember, the Archimedean regulator is defined the same way. You take sort of all the embeddings into Q bar, and then you fix some embedding of Q bar into C instead of CP, and then you take the complex absolute value, right? So that's what I call the Archimedean regulator. And we know this this matrix has rank R, right? So this is proven using some notion of ordering, right? The fact that you can choose units such that their absolute value is 1 in one embedding and less than 1 in all the other embedding. This is some sort of Minkowski method where we're using some ordering on the real numbers. And so that's what we don't have an analog of in the p-adic numbers to mimic that proof. So we're going to use this kind of as a black box, the fact that the Archimedean regulator is non-vanishing, that this matrix, if I replace all the p-adic logs with Archimedean logs, has rank R. Okay, but then if you look at the corresponding submatrix of the Leopold matrix, and I have this M and M prime. If I could show that this matrix has determinant that's non-vanishing, then the p-adic matrix has rank at least R. Okay. Okay. Now, if the rank of the Leopold matrix is less than R over 2, then the same is true for this submatrix that I chose. And then the Walsh-Master theorem implies that there exists, so the p-adic version, the Walsh-Master theorem, tells me that there exists sort of a rational change of basis on the left and right, such that this matrix has an upper right zero block with dimension m times m prime. Now, if you apply this same change of basis, it does the same linear combinations of the rows and columns of the Archimedean matrix, right? Then you get an Archimedean matrix. Then it has the same property because you're getting sort of where you have the p-adic logs, you have the Archimedean logs, okay? And so saying that the p-adic log of something is 0 is basically in the setting that I have is saying that that number is equal to 1, which means that in the Archimedean case it's equal to 1. So you're taking the Archimedean log and it's also 0. Okay, so that implies that the determinant of this m prime is 0, because this is what I was saying, that this 0 block is so big that it implies that the determinant of that matrix is 0. And now P and Q are invertible matrices, so that means that the determinant of m prime is 0. But we know the determinant of m prime is not 0 because the Archimedean regulator is non-vanishing. So that's the end of the proof. So it's kind of cool. We show that the fact that the Archimedean regulator, the Archimedean matrix, if you will, has full rank implies that the p-adic regulator has at least half the rank. Okay. All right. So I'm going to end there, and